We have most recently had the good fortune of studying multivariable functions. And we've in particular studied functions like this: z equals f of xy equals x squared plus y squared. This is a function of two independent variables, and it gives us a surface, in particular, a paraboloid. Now, then we got into this idea of the partial derivative, where we fix one variable. For example, we'll fix y and view it as a constant, and then take the derivative with respect to x. That's a partial derivative with respect to x, partial z with respect to x. And that gives us the slope of tangents in the x direction. Then we looked at the same thing for the y's. We fixed x, took the derivative with respect to y, and we call that the partial of z with respect to y. And that gives us the slope in the y direction. Then we broadened it out a little bit and said, okay, well, let's just not limit ourselves to the x and the y directions. Let's think about any direction we want, and we'll call that the directional derivative. What I want to do here is go through and I want to find equations for tangents in the x direction and in the y direction and in the direction of the gradient for this function right here. So, and let's do it at this point. Let's do it at the point 1, 2, 5. If x is 1 and y is 2, then z has to be 5. So let's do that. Let's talk about the line in the x direction. So first thing we need is we need to get the partial so I can find how much z is changing with respect to x. In other words, as we do a unit of run in the x direction, how much rise goes in the z direction. That's what we want to get. And that's what this partial will tell us. So let's do the partial with respect to x, and we get 2x. Now, if we plug in the 1, 2, that's just going to give us 2. So here's what this tells us, that for every unit change in the x direction, the change in the z direction is going to be 2 times that. It's going to be 2, right? So to write an equation for a tangent, what we need is we need a vector parallel to that tangent, and we also need a point. Well, we've got the point right here. And here's what we can do. I can say, okay, the vector is going to be, well, let me do this. The vector is going to be 1, and y, we're in the direction of x, so we can just make y 0. We just want a vector parallel in the x direction. And then this over here is going to be 2. The z component is going to be 2. So now we have a point and we have a vector. So here we go. We can say x is equal to 1t, see, the 1t plus 1, see, at the point. Y is equal to 0t plus 2. And z is equal to 2t plus 5. Plus 5. And there is our equation. That's our set of parametric equations that will give us the equation for that tangent. Now let's look at that right here. Let me blow this up a little bit. Move it down here where we can see what's going on with it. There it is. Okay. You can see the point right here, and you can see the tangent, and I went ahead and put a plane in there. This is the plane y equals 2. So you can see we've got that plane. It just cuts the paraboloid, and so you can see that this tangent is in that plane. So when we cut that paraboloid, it made a little trace up here. Okay. So there we have the tangent in the x direction. Now let's look at the tangent in the y direction. Okay, so we still got the same point. Okay, still got the same point, and it is 1, 2, 5. Now I want to find the partial with respect to y this time, and it's 2y, of course. And now the point is going to be 1, 2, it's going to be 4. Now we've got our point, we need a vector. So here's what we do. Our vector this time is going to be, for the x, we'll just do a 0. Then for the y, let's see what we've got here. We'll just put a 1. Now, for every unit of run in the y direction, z has 4 units of change, 4 units in the z direction. And notice what this is. This right here is just f partial with respect to y, 1, 2. Now that would be the same thing up here. I don't know if I focused on that, but this one right here is the partial with respect to x, 1, 2. That's what that is. So to be more general. Now we can write our equation for this one, our equation for the line, because we've got the point and we've got the parallel vector. So here we go. We've got x is equal to 0t plus 1, 1t plus 2, and then 4t plus 5. And that's our set of parametric equations. And here is what the graph would look like. If we sketched it out. And this time I put the plane at x equals 1, and you can see the point right here. So everything is mapped out. The point, I don't know if you can see it right there. There's the point. Okay. So there we have our tangent in the y direction, and I'll call that Ly. Now, let's for the next step, let's look at the directional derivative one. With this one, we have a choice which direction we go. So we've got our function here, and I want to find the tangent in the direction of the gradient, the direction for the greatest increase. So let's find the gradient. So I'm going to find the gradient here. It's going to be 2x and then 2y. Okay, there's the gradient. And now I plug in the values. My point is 1, 2, so x is 1 and y is 2. So I've got 2 and 4. That's the direction we're going to calculate the directional derivative in. Now, remember we use the unit vector in finding the directional derivative. So let me make the unit vector here. It's going to be 2 over the square root of 20 and 4 over the square root of 20, because the magnitude of this vector 2, 4 is 2 squared plus 4 squared. That's 20. And then I take the square root. And of course, this will reduce. If I reduce the radical, I'll get 1 over the square root of 5 and then 2 over the square root of 5, just reducing that radical. Now we have our vector, and we're ready at this point to get the directional derivative. So here we go. Here's the directional derivative in the direction of u. So here we go. We're going to take 2x times 1 over the square root of 5 plus 2y times 2 over the square root of 5. There we go. And then I plug in the 1, 2, and let's see what we got here. Okay, we've got 2 over the square root of 5 plus, let's see here, putting in a 2 for the y, I get 4, 8 over the square root of 5. And that would be 10 over the square root of 5. Okay. Now, at this point, we're ready to find that tangent line. So we need our vector. We've got our point. Our point is 1, 2, 5. Now let's look at and see what our vector is going to be. Our vector is going to be, for this one, the directional derivative, I'm going to take the x component from the vector that we use, the direction, the gradient. So I've got 1 over the square root of 5. And then I take the y component for the y part of the vector. And then for the z, I'm going to put the directional derivative, 10 over the square root of 5. So realize what we're saying here. For every unit we move along the path of the gradient, if there's a line down there, for every unit we move along that path, if that's the run, then we have this much rise in the z direction. So this much run in the gradient direction yields this much rise in the z direction. So there's our vector, and we have our point. Our point is 1, 2, 5. So at this time, we're ready to go ahead and make our line. We've got x is equal to 1 over the square root of 5, t plus 1. Y is equal to 2 over the square root of 5, t plus 2. And then z is going to be 10 over the square root of 5, t plus 5. And there is our equation for the line. Now I went ahead and I graphed this for you. Let's bring this down. Maybe extend the page a little bit. And here's what we've got. Here's what the graph looks like. And what I've done there is I've went ahead and put the plane in there. I've put the tangent plane along with the line. And we can go back and we can actually look at the graph. Here it is, where I graphed it out. And you can see the tangent plane there, the line that is on that plane that's tangent at the point A. Now, what we're going to do next in the next video is we're going to figure out, well, how do we get that tangent plane? Because I put it there, but I really didn't show you how to do it. So that's what's coming up next.